looking at example 2 on the worksheet for section 7.3. So on this one, hopefully you've read a bit about the definite integral and stuff here. What is a definite integral? It's this idea of approximating the area under a curve with several rectangles, adding up the areas of all those rectangles, and then we just take the limit as the number of rectangles approaches infinity. But for these ones here, we're going to approximate it using 4 rectangles again. So we'll go through this kind of the longer way, or using approximations instead of finding the exact area. After this, then we'll figure out that we can actually do this like this anyway, that with geometric shapes. Like in this case, it'll be a triangle, but here we're going to do the rectangular approximations with midpoints. So we'll see what happens when we do that. All right, so here's the that's the integral that we're looking for. I've got the xy axis set up here. The function is going to look something like this, a linear function between these 2 points. So we're going to approximate this with midpoints again. That means we want to take a look at the midpoint of each of these, figure out what that is. So that's going to be 1/2 here, 3 halves, 5 halves, and 7 halves. So these are the midpoints for each subinterval. It says 4 of them, and so since we're going from 1 to 4, each one has width 1. So each one has a width 1, and we're going to be approximating that height of each one with the midpoint. So it's going to look something like this for the first one. Midpoint of the second one is here. It's going to look something like this, the second rectangle. Third one, its midpoint is 5 halves. Its rectangle will look something like this. And then the last one, midpoint here. So the rectangle there will look something like this. Okay, so what we want to do is just approximate the area under the curve by adding up the areas of all of these approximating rectangles. So the first rectangle has area, I'm just going to say total area here. First rectangle, what is its area? Well, its width is 1, so the area is basically just the height. So f of 1/2, plug in 1/2 to this thing, 1/2 times 4 is 2, so 2 is the area of the first one. Second one they all have width 1, so again, the height is just determined by, or the area is just determined by what is the height. It's just the height times the width, but the width is 1. So f of 3 halves, if I plug that in there, 3 halves times 4, and 6. And then the third one, 5 halves is the height, that's what we plug into the function. So 5 halves times 4 is 10. And then finally 7 halves, and we'll put that in the function, we get the height of the fourth one, so that'll be, let's see, 14. So add these all up, and that gives the approximation of the area under the curve. So it's going to be 8 plus 10, that's 18, plus 14. 18 plus 14, that's 32. So the approximate area under this curve between 0 and 4 is 32. Now, if you'll notice, in fact, 32 happens to be the exact area under this curve, because like I said earlier, you can actually do this by geometric argument here, meaning that you just look at the shape overall of the area under the curve, and that's clearly a triangle. How do you find the area of a triangle? 1/2 of the base, which is 4, times the height, which is 16. So if you do that, 1/2 times 4 times 16, you will indeed get 32. So this midpoint approximation actually does a perfect job on linear functions. But that's only going to happen for linear functions because of the nice symmetry that you have going on here. Basically, if you use a midpoint, then the over approximation, that little area right there, for example, on each rectangle is exactly canceled by that little area right there. That's not going to happen on something like a parabola, but on a linear function, the midpoint rule actually gives the exact area under the curve.